Mr. Burkamp, do you want a dog?
I take the German Shepherd. That's
like
the
a
idea.
golden German Shepherd. It was really like
Like,
black.
which is like, I got the highest.
Really?
one for that.
Except on his face.
Like,
Yeah, big old head.
it's like $20,000.
Okay. Don't start though.
To me, these are good news days because you learn a lot and then you don't have homework.
Ooh, get him. Get him.
I know what I say. You know. This isn't my
I
first
see you.
rodeo.
I see you.
Nick, God.
Yeah, pretty much any given day you walk in, what do you want to talk? Okay, here we go. You know.
Really.
Okay.
The easiest way to make a metal bucket.
What?
I said just whatever you
Dude,
want.
I'm
You
trying
just,
to leave.
someone tells you just come in and
Let
teach
it
it.
go, buddy.
That's the easiest way to make a metal bucket.
Take a flat piece of metal and metal touch and,
What type of metal? It's not aluminum.
yeah, what do you want the bucket to do?
Hold a lot of water.
Aluminum. Okay, you have to heat up the water or just hold it? You want to heat it or not?
Yes, you have to heat it up.
Okay. Well, that completely changes the type of metal.
Duh, you gotta heat it up.
Okay,
That's a
anyway,
pot, not a bucket.
so Mad Max, here we go.
Okay,
Are we really going? Seriously?
only for a minute.
Okay,
Come on, comic.
so what we're going to work through today are the equations relating to planetary motion and how they work and how they don't work and the mistakes you'll make and hopefully the mistakes you won't make. So the trade-off of the day is you don't have any homework, but the assignment that you get tomorrow, and this only happens in this assignment because it's so long and the problems are so complex. The assignment I'm going to give you tomorrow is actually due on the day of the test on Thursday. Okay, so you're actually going to get 2 days to work on the assignment if that gives you any indication. So if you talk to any of my former students, just say, oh, we got the gravity assignment, and they're going to go, that sucks. Okay, so I'm just telling you. I mean, the math isn't that tough, but you're going to be dealing with very complex calculations like cubes and cube roots and squaring, and there's a whole bunch of stuff that you have to pay attention to. But thankfully, you will have calculators, and it makes life much simpler. Okay, so let's kind of start off where we were. So here's the Earth, and who were we using on Friday? Matt.
I was the sun like 2 months ago, man.
We'll
You're still the
revisit
sun,
that. Okay.
I mean, it's not that big of a deal to me. You can choose another sun if you want to.
Okay. Okay, but we need the Earth, not the Sun for now.
Yeah, no, it's fine. I'm fine with not
The chosen
participating.
one. The chosen son.
I'm good, man.
Okay, so this is what we talked about on Friday. So one option to find the gravitational attraction between Mary and the Earth would be to take big G, the universal gravitational constant, times the mass of a single proton, times the mass of every particle, individual particle that makes up the Earth, divide that by the distance squared, so we'd have to know the mass of every single electron, proton, neutron that makes up the Earth, and the mass of a single proton on the end of the index finger on Mary's finger. Then we're going to do that for every particle that makes up Mary, and we're going to do this again and again and again and again and again. It would take a lifetime of lifetimes of calculations to do this, and you still wouldn't be done. So physicists said, okay, there's got to be an easier way to do this than every calculation. So I said, okay, we're going to shrink Mary down to a point mass. Okay, physicists are known for point mass calculations. So in other words, we're going to take Mary and we're going to condense her down until she is a single infinitely dense point with the same mass. Okay, mass is still 100 kilograms. Then we're going to do that with the Earth. So then we're going to shrink the Earth down to a single point. So imagine that we're going to condense the Earth down into a single point. Now, this is where the calculations become much simpler. So now, instead of doing this calculation again and again and again and again and again for every particle, now we just have to do the calculation once, because we're treating Mary as a single particle with a mass of 100 kilograms, and we're treating the Earth as a single particle with a mass of 5.979 times 10 to the 24th kilograms. Now, here's what's important. The distance between them, you kind of have to visualize this being the radius of the Earth. So the distance between them is still the radius of the Earth. Okay, we're not touching. Okay, so we're taking the Earth as being here, Mary being here. So they're still separated by the radius of the Earth, even though we've condensed them into infinitely small points. Now, at this point, now the math becomes simpler. Because instead of doing this again and again and again and again, now I only have to do it once. Okay? So anytime you have the mass of two particles and the distance, you can always find the gravitational force between them. So here's what we're going to do. We're going to go F equals big G, 6.67, times 10 to the minus 11 newtons meters squared over kilograms squared. Mass of Mary is 100 kilograms. Mass of the Earth, 5.979 times 10 to the 24th kilograms. And then we're going to divide that by the radius of the Earth, 6.3713 times 10 to the 6 meters. And that's going to get squared. Okay? So, if you're going to store numbers in your calculator, which I would recommend, I'd store this value of big G, I'd store the mass of the Earth, 5.979 times 10 to the 24th, and I'd store the radius of the Earth. These are on your equation sheets. They're in the top left-hand corner. It isn't like you have to have these memorized, okay? You're going to have them available to you. But this just saves you punching them in every time. And again, when you punch these in, if you're going to store them, do not punch in times 10. Use that EE key or you're going to get answers that make no sense whatsoever. Okay, because it's going to completely jack up your order of operations. Use that EE key. Now, before you even touch a calculator, okay, I want to get an idea of what's known as the order of magnitude. I just want to get an idea, okay? I just want an idea of what this answer should be based upon the exponents, okay? That's all, okay? So, 100, that's 10 to the second. So, if I take 10 to the negative 11 times 10 to the 24th, I get 10 to the 13th. 10 to the 13th times 10 to the second gives me 10 to the 50th. So, just on order of magnitude alone, I'm about 10 to the 15th on top, okay? Landon, when I square 10 to the 6th, what do I get? It's either 10 to the 8th or 10 to the 12th. Good call, 10 to the 12th. So Garrett, if I take 10 to the 12th and divide it by, or 10 to the 15th and divide it by 10 to the 12th, what do I get?
10 to the 3rd.
10 to the 3rd. Thank you. Now, this just gives me a ballpark order of magnitude of where I should end up. Okay? That's all. It's an order of magnitude. So if I do this calculation and I get 10 to the 6th, I've done something wrong. If I do this calculation and I get 10 to the negative 4th, I have done something wrong. Okay? So this just tells me roughly where I should be. Now, trust me on this. In this unit, you have the potential to get answers that make absolutely no physical sense, more so than any other unit you're going to do. Mainly because you're squaring and cubing all of these really, really big numbers. Okay? You name the answer, I've seen it in the years of teaching this. I've seen answers longer than the universe itself has existed. I've seen answers of like 10 to the negative 6 seconds on how long it takes the lunar command module to orbit all the way around the moon. I've gotten mass of objects bigger than the entire Milky Way galaxy itself. Okay? I've gotten an orbital radius for something orbiting the Earth that literally puts it outside the Milky Way galaxy itself. Okay? I've gotten velocities of orbiting objects faster than the speed of light. Now, here's thinking you all giggle, go, Mr. Burkett, we won't do that, whatever. Okay, you lie. Because here's what's going to happen, is that you're going to blissfully punch numbers into that calculator. The oracle is going to give you an answer, and you're going to write it down, because this is what the oracle says. And you're not going to pay any attention to whether or not it actually makes any sense. Because that's what you all have been trained to do, is to punch numbers into a calculator, the oracle speaks, and you write them down. Your brain engaged in that process has never been stressed to you. Let me give you a hint. Stress that step. Okay? Stress the step of looking at an answer, seeing if it makes sense before you write it on the paper. Yes, that is an added step, but you all can handle it. I have the utmost faith in all of you that you can handle that extra step. Okay, now, give me an answer. By the way, make sure that you can do this on your calculator. This is when you want to try this, to make sure that you have the numbers stored and make sure that you know how to run that calculator that you have. What'd you get?
983.
983?
92.
I'm rounds up.
982.
982.
Okay, 982, 983, something like that, right? And that matches with what we said, right? We should say get 10 to the third. We got 10 to the second, but it's a big 10 to the second. You know, it's almost 1,000. So, it seems like a reasonable answer, right? Everybody cool with how we got this? If you're not getting this answer, figure out what you're doing wrong, okay? Because don't ignore it, go, oh, it'll fix itself. No, trust me, it won't. So make sure that you can do this. Now, temporarily, I want you to act like this does not exist. We'll get back to it. So pretend that that's gone. And that's the beauty of my board. We can just do that. So let's say that you're in this class on the very second day in here and we're doing the spring lab. And I'm going to tell you that we're going to suspend a 100 kilogram mass from the end of the spring. Okay? It's pretty big, okay? Because you guys have 1 kilogram, this is 100 kilograms, right? And the very first lab, we wanted to figure out the gravitational pull. So how did you all, on that second day you were in here, how did you all calculate, and since then, how would you calculate the gravitational pull between the 100 kilogram mass and this rock that we're on? What would you do? Take 100 kilograms times 9.8 meters per second squared. And oddly enough, you get 980 newtons. When y'all did the good calculations, you got what? 982. Coincidence that they're the same number? No. Because what's creating the gravitational, what's creating weight? Gravity. So here's two ways that you can calculate the gravitational attraction between any two objects. Okay? One option is that you take the mass and you multiply it by 9.8 meters per second squared. Okay? You can get an answer, 980 newtons. It's simple, it's nice. Multiply it by 9.8. So, now, the other thing that you can do is you can take that same mass, multiply it by the mass of the Earth, multiply it by 6.67 times 10 to the negative 11th, and divide it by the radius of the Earth squared. Now, imagine on the second day of class, I said, okay, here's the story, kids. Every time you calculate the gravitational attraction between an object and the Earth, you've got to take the mass times 6.67 times 10 to the negative 11th times 5.979 times 10 to the 24th and divided by this number squared. You'll all be going, seriously, for every calculation, this is what we have to do, right? And you all would have flipped out. It's like, oh my God, physics is so tough. Okay? This is why I didn't tell you all this on the second day, because you all would have been like, whoa, what does this even mean? Okay? Now that you kind of handle the information, oh, okay, yeah, now that makes sense. But here's the ultimate truth, okay? And this is where this plays out. Notice if you calculate the gravitational attraction between Mary and the Earth, you get 982 newtons. This is using the full-blown Monty, here we go, okay? Or, you can take 100 kilograms times 9.8 and you can get the same answer. So here's the truth, and this is what led to one of the most profound observations that we ever made in physics, is that there's two ways you can calculate the gravitational attraction between Mary and the Earth. You can use the mass of the Mary, how about that? mass of Mary times G, or you can take big G, mass of Mary, times the mass of the Earth, mass of the Earth over r squared. Now, nothing against Mary, because this would happen to everybody. But what's going to happen to Mary? She's over here, she's over here.
Cancel.
That's low.
Mary cancels out of the equation. Okay, nothing personal, Mary. It happens to everybody. It's good. It's just not you. Okay. Well, it's just me. No, everybody. So here's what you're left with. Little g equals big G mass of the Earth over r squared. Now, so at this point, a huge aha moment happened in the scientific community. Because now they could look back at the works of Galileo. Because what did Galileo do? What observation was he most famous for?
They follow the same.
Everything falls at the same rate, right? He had the small cannonball, he had the large cannonball, the entire piece he drops it, right? Which is the basis of the lab that you all did with 1 penny, 5 pennies, and 10 pennies, right? So here's what's important. This is why everything accelerates at the same rate. This is the most important part. This is why everything accelerates at the same rate. Because the only thing that determines your gravitational acceleration, this is what little g is, so this equation gets you the gravitational acceleration, is that notice the mass of what is falling isn't in the equation. It's not there. To calculate little g, you need the mass of whatever the object is falling towards and how far you are from the center of that object. That's it. What you drop doesn't matter. So if it was Mary, the bowling ball, a golf ball, and we drop them all, guess what? They're all going to end up accelerating at the same rate. Notice that entire acceleration test dealing with gravity, okay? Back when we just had acceleration, I never gave you the mass of the object. You know why? Doesn't matter. Okay, it cancels out. Now, I want to point out a big difference between this big G and this little g. This big G is a constant. Okay, in physics, when you see uppercase letters, that means it's a constant. That means it's invariant. Little g changes. So if you look at this, you're dividing by r squared. So what that means is if you go to Denver, slightly higher altitude, little g in Denver is actually a little bit smaller than it is here on Earth. Excuse me, than here in Mesoamerica. Oh, they're also on Earth. Okay, depending upon where you are on those. Now, you climb to the top of Mount Everest, right? What's going to happen to that value of r?
Smaller.
It's going to get... No, you climb to the top of Mount Everest, the value of r is going to get bigger, so g is going to become smaller. So if you were to look at the graph, okay, of little g, and let's say here's 9.8 meters per second squared, and this is radius, okay? And obviously you're going to start at like the radius of the Earth. So what this means is if you, right here, if you plug in big G, the mass of the Earth, and the radius of the Earth, you're going to generate a value of 9.8 meters per second squared. Okay? That's what the number means. So if you were to look at a graph, and if you're standing right here on the surface of the Earth, you would have a value of 9.8 meters per second squared. So here's the question. As I go further and further and further, so here's the radius of the Earth. So as I go further and further and further away from the center of the Earth, what's this graph going to look like?
Sloping downwards.
Downward sloping line, right? So it's going to go something like this. Now, notice that this is r squared. So any changes of r produce a huge value in terms of this. Now, here's one of the most common misconceptions that everybody has. It's like, oh, well, this graph explains why people in the International Space Station, or when they're in orbit, they float because they're in 0 G. No, stop, no, bad, don't. Okay. To give you some perspective, okay, if this was the actual size of the Earth, you can shrink it down. when things are in orbit, they're about a half, in your Earth orbit, they're about a ½ inch above the surface of the Earth. Okay, that's it. So when you look at this, and we'll calculate this later, little g does not go to 0. Because if little g goes to 0, guess what? That means you're not accelerating towards the Earth. If you're not accelerating towards the Earth, what are you doing?
Flying on a straight line.
Yeah. Okay, that got a little macabre. Okay, but certainly you're going to go off in a straight line. So the worst thing that can happen is if you're in the International Space Station, you get a phone call from NASA going, hey, we don't know why, but we don't have gravity anymore. At that point, you're going, we are so screwed. Because you are gone. It's just like letting go of a rubber stopper. So what happens, and I'll explain this in just a second, is that things appear to float because they're in a state of free fall. So to give you like another perspective on this whole deal, there's nothing magical about outer space in terms of that's why things float. You could launch things right at the surface of the Earth, okay? You could do it. But the problem is that our atmosphere would cause it to burn up so quickly because of the heating. So if we didn't have an atmosphere, literally, you could launch satellites just high enough that all they have to do is clear the mountain ranges. Okay, that's all. So you could look up and you could see them, you could see satellites going around at the same altitude as an airplane flies. Okay, you could do it. So there's nothing magical about outer space. The only thing that's magical about it in terms of our atmosphere is that you're above it. Now, speaking of our atmosphere, and this is why this rock that we're on is so strange. If you take like an apple, we'll talk about Newton and his apple in just a second. If you take an apple and you cut it in half, and you've got that red layer of skin, okay? If the Earth was the size of the apple, that would be our atmosphere, okay? Is that layer on the apple. So the only thing that allows us to exist on this strange rock that we're on is a relative thin layer of gas that protects us from charged particles, ultraviolet rays, X-rays, allows us to have an atmosphere, allows us to breathe, allows us to have weather, okay? So out of this entire apple, we exist because of that thin red layer on that same scale. So it's kind of a cool thing when you think about it. So if you're going to orbit, you just have to get it above that layer on the apple to make that thing be in orbit. Now, let me explain how Newton viewed the orbit. So this is not the scale, but here's the Earth. Okay? And let's say up here you've got a mountain, right? And on top of the mountain, there is a cannon. Okay? And being civilized people, we figured out how to fire the cannon. And that's what cannons do, is they fire cannonballs. So you're going to fire the cannonball, because that's what they cannon do. And it's going to land out here. Now, being adventurous souls in the human race, we realize, well, if that's good, more cannon or more gunpowder has to be better. Okay, so let's fire it a little bit faster. Okay, and it's going to go something like this. And then you go, well, if that's good, more gunpowder is going to be better. So then you go something like this. So it goes further and further and further before it lands. So if you could make it go fast enough, what would it do? Come back around. Ah. Otherwise known as being in orbit. Okay? And it's going to back and hit you in the head. If you're smart enough to fire the cannon, you're probably smart enough to duck. Okay? I'm just guessing. So what that means, and this would be the ultimate like physics demo, is that let's say that I could take, I don't know, this gremlin, right? And if I throw it fast enough, if I throw it just a little bit of velocity, it travels a certain distance before it lands. So the faster I throw it, what's going to happen to the distance it travels before it lands? It increases, right? And the faster and faster and faster I throw it, the farther and farther and farther it's going to go before it lands. So here's your odd geometric fact for the Earth. For every 8,000 kilometers or 8,000 meters, excuse me, which is 8 kilometers, The Earth curves out from underneath you about 4.9 meters, which is about twice as high as the sea level. So here's the significance of the 4.9 meters. Like, well, Burkamp, who cares about the 4.9 meters? Here's why this is important. If you look at distance equals 1/2 AT squared plus V naught time. So when I throw this golf ball, okay, if I can throw it fast enough, and I'm going to throw it horizontally, what's my initial vertical velocity? I'm going to throw it completely horizontally. What's my initial vertical velocity? Zero. Now, if I plug in 1 second, 1 second squared times 9.8 times a half gets me 4.9. So what that means that if you let an object fall for 1 second, it's going to fall 4.9 meters. So if you're traveling at 8,000 meters per second, every second that goes by, the Earth is going to curve out from underneath you 4.9 meters, which is how far it's going to fall in a state of free fall. So if you can get going at 8,000 meters per second, the Earth is just going to continuously curve out from underneath you. So, and it would take, at where we're at, it would take about an hour and a half. So this would be the ultimate physics demo. Because I could take this golf ball, I could go outside and I'm going to throw it right at the beginning of class. And then I'm going to come in, give a lecture, because that's what I do, right? And then after about an hour and a half, we're going to go back outside, and then I'm going to catch that golf ball as it comes back around in my hand. Because that's about, oh, it would be the ultimate physics demo. It would be so cool.
That's going to be in the future. Colin.
Okay, the problem is, if we have, as long as we have an atmosphere, we really can't do it.
Oh, man.
Now, to give you an idea of how fast this is, 8,000 meters per second is about roughly about 5 miles per second. Okay, so to give you some perspective, imagine that you're up here at 53rd and Rock Road. Okay, so if you go down to 45th, and then 37th, 29th, 21st, 13th Street. So you're going from 53rd and Mays Road to 13th and Mays Road in 1 second.
So just so nice sometimes.
Okay, the problem is that you would burn up in the atmosphere. Okay, small problem.
What if you're sitting in ice?
The ice is going to boil and vaporize you anyway. Okay.
Speaking of ice, is snow ice?
Yes.
You guys ever any snow on the walls?
Okay, it's just really pretty ice.
Thank you.
Okay. All right. So this is why things have to be going so fast to be in orbit. So here's what I want you to realize, is that when you see things floating in space, they're not in zero gravity. They're just in this continuous state of free fall around the Earth. Okay? So when you see something, don't go, oh, they're in zero gravity. No. Because if they were in zero gravity, doink, that's the action that you got going. Okay? Now, I don't know if the moon is still up, but it was first block. So I don't know if this is still up or not, but let's make a quick road trip outside and we'll see.
Should I bring What?
I lost my fish net.
He's saying he sounds like an elephant.
It's because he's got the trunk.
I had to struggle with that when I was like, not really. Okay, so let's talk about the significance of this equation. So Henry Cavendish was the first one that found out the numeric value of G. So we talked about what he did last Friday. He had the metal spheres and he measured how much force it took. So here's the cool thing about what Cavendish was able to do at that point. So at that point, this is after Newton had published his works and everything. So everybody knew the acceleration due to gravity. So they knew that number. We've known the radius of the Earth since antiquity, and that's a whole other story about shadows and how at different points on the Earth. Okay. At that point, Cavendish found the numeric value of big G, so he was the first one to figure out the mass of the Earth. So his claim to fame was that he weighed the Earth. So he was the first one to be able to say, okay, look, I know everything except for the mass of the Earth. This is what we've got. So if you look at all of the data, when you ask your phone, Siri, what is the mass of Saturn, or anything like that, it isn't like, you know, we developed the telescope when we could look at Saturn or Jupiter or the moon, and we could find like this little information plate that's stamped on these planets says, oh, this is when they were manufactured, here's their atmosphere, this is, you know, their mass, this is their diameter, okay? We had to figure all of this stuff out. So this is one of the things you could do is that you look at the influence that the gravitational field has on other objects, and then you work backwards. So one of the first experiments that they did with the Apollo 11 mission that landed on the moon is that they took along a pendulum, okay? And you're going, seriously, you all traveled to the moon and you took a pendulum. Really? But here's the reason why. Period of a pendulum is 2 pi times the square root of L over G. So if you have a pendulum, and you can measure its period, and you know its length, you can solve for the gravitational acceleration on that planet. Once you know that value, then you can plug that into here. And then if you know the radius of the moon, then you can figure out the mass of the moon. So this is what one of the first things that they did is that we found the mass of the moon. By setting up a pendulum, measuring the value of little g, and we plug that into that equation, voila, we got the mass of the moon. So you can do the same thing with the Earth. If you want to know a very precise measurement of g, actually use a pendulum. Get that value, plug that in, voila, here's the mass of the Earth. So if we ever lose the mass of the Earth, you ask Siri, say, hey, what's the mass of the Earth? Siri goes, I don't know, data has been lost. Okay, here's how you can get the data back and save humanity. Set up the pendulum, measure the value of little g, plug it into that equation, we can reestablish the mass of the Earth, problem solved. Now, here's what you want to look at in terms of this value of little g. What, Greg?
Is the r squared, sorry, it's might be stupid, is that, that's still just the orbital radius, right?
Yes, but it's from the center. Listen to me,
center.
listen to me, listen to me.
Let me write that down.
Anytime you're using r, it is not a surface-to-surface distance. It is a center-to-center distance. Just like with Mary, we said Mary was a point mass, and we said the Earth was a point mass. Okay? So anytime you do a calculation involving r, it is not a surface-to-surface distance. It is a center-to-center distance because you're treating everything as a point mass. Okay? I cannot emphasize this enough. It is not a surface-to-surface distance, but a center-to-center distance. Okay. So this is kind of handy in terms of trying to figure out, oh, okay, well, what can we do? So here's what I want you to understand in terms of like Newton and the moon. So here's what Newton realizes that, okay, here's the Earth, and he had an apple, okay, according to the story goes, and the apple fell, and it had an acceleration of 9.8 meters per second squared. And then he said, okay, well, here's this random rock that's orbiting a bigger rock that happens to be orbiting a star, okay? And this, at the end of the story, that's what the Earth and Moon and the star and the Sun is. It's a big rock, a little rock, and a star, okay? And we're orbiting in an average galaxy. So, what Newton realized, he says, okay, hey, look, the Moon is accelerating towards the Earth. Now, how did he know that the Moon was accelerating towards the Earth?
Changes direction.
Yeah, because if the Moon wasn't accelerating towards the Earth, what would happen? We wouldn't have a moon. Okay, it would have been lost a long time ago, right? Long time ago. So he realized that it had to be accelerating towards the moon. But is the acceleration of the moon towards the Earth going to be bigger or smaller than 9.8 meters per second squared?
Smaller.
Bigger, smaller, or the exact same?
Oh, thank you. If it was bigger,
Wait, it would be smaller.
wouldn't it be
Because the R
closer?
squared would make it.
What'd you say, Madeline?
I said would be smaller because the R squared would, the R would be bigger, so the R squared would make it smaller.
Okay, so little g is what's creating the centripetal acceleration, which is going to be the whole point of today's lecture in just a second. And that's big G m over r squared, right? And this is the mass of the Earth. So if you go exactly what Madeline said, when you're way out here, okay, what's happened to that value of r?
It's increased.
radius has gotten a lot bigger, so the value of g has become smaller. So here's what, and when you do this calculation, okay, it's a really small number. But that's okay. So what this means is if you could stand out here and just drop Hank the bowling ball. In other words, if you could just take Hank here out into space and just let go of him at the orbital radius of the moon, this Hank is going to begin to accelerate towards the Earth, just like it would if I dropped it right here. But that acceleration, because it's so far away, is going to be such a small number. But here's what's important. The acceleration that it would experience if you just drop it is the exact same as the centripetal acceleration it experiences to go around in a circle. Two numbers that are exactly the same. Okay? They are exactly the same. So, because gravity doesn't care. It's like gravity doesn't care that you're moving in a circle. It's still going to make you accelerate towards the Earth. Now, don't flip out and go home to Mom, Dad. Oh my God, Mom, Dad, the moon is accelerating towards the Earth. Yeah, it's okay. It's okay. Don't flip out. Now, it would get weird if you could actually stop the moon. I don't recommend this. But if we could actually stop the moon in its orbit, what would happen is that the moon would begin to accelerate towards the Earth. Okay? In other words, if you could just stop the moon and just let it sit here, it would begin to drift towards the Earth. Great.
So why wouldn't the bowling ball have the same, like, orbital, I guess, acceleration?
It would. I'm just telling. But the point I said with the bowling ball is if you could just stop it right here. In other words, if not, I'm not talking about.
It would orbit the same.
Oh, it would. It would
Okay.
orbit the exact same if it was going the same speed as the moon was.
Yeah.
But I'm just saying, if you just took the bowling ball out, way out here, okay, to the where the moon orbits and let go of it, it would slowly begin to drift towards the Earth. Now, as it gets closer, what's going to happen to that acceleration?
It'll get larger.
It'll get larger because the radius is continuously getting smaller and smaller and smaller. Okay, but it wouldn't be cool because you could see the moon, and then over a period of time, the moon would be getting closer and closer and closer and closer and closer and closer and closer.
It's like Despicable Me.
Okay.
Have you watched the movies? They steal the moon.
Yeah. Yeah. It's been a
What would
while.
really happen?
Yeah.
If the moon is gone,
Yeah, like there's no.
or it would affect us primarily because it stabilizes the tilt on our axis.
And the wind.
So it's like a harmonic. It keeps us stable. So we would begin to wobble more on our axis,
How would we feel that on Earth?
and we also wouldn't have tides.
Yeah.
So the only reason we have tides is because of the moon.
What does tides necessarily do?
Well, from an evolutionary standpoint, tides were a good thing because if you subscribe to the idea that evolution occurred in water, so what happened when you had tides is that you had an exchange of water in and out along those tidal regions, and then that then allowed for like the mixing of nutrients. Otherwise, it would have just been like a stable, dead body of water where those nutrients would have never mixed.
Gotcha.
So that's the biggest thing that it gets us. Okay, cool with this. All right. So this just tells you the gravitational acceleration on a planet. Now, speaking of satellites, let's say that here's the Earth, okay, and here's a satellite, okay, all right. This could be going around the Earth. And let's say that it's orbiting at 200 kilometers above their surface, okay, which is something close to like a normal orbital radius. So to give you some perspective, 200 kilometers is about the distance from here to Emporia, okay? So it is a huge distance to make for something to have an orbital radius of like 200 kilometers. So imagine that you could build like a ladder from here to Emporia, and then take that ladder and then stand it up. That's, if you could stand that ladder up and stand on the end of that ladder, you would be tall enough then that you could see like the satellites go by, right? So this isn't like a huge distance for something to be in orbit, okay? It's really not that far, which is why if you ever go out into the night sky, especially if you're away from the city lights and once your eyes get acclimated, you can see and track satellites as they go by just with your naked eye. Because you'll see like these flashing bits of light going by really, really fast. So it's really easy to see satellites at night. If you never have, but you kind of have to be in like in a darkened area outside the city. If you go out there, you can see satellites going overhead. Okay, so we're ordering at about 200 kilometers. And here's one of the most important ideas that we've got. Is the satellite undergoing centripetal acceleration?
Yes.
Yes. Which requires a centripetal force. And what's the direction of that force?
90 degrees to the
Inward.
At a 90-degree angle to the
At a
velocity.
90-degree angle to the
Velocity.
instantaneous velocity vector. Now, I promise you on the test, which is coming up this Thursday, okay, and yes, I know it's the night after Halloween, and no, I don't care. I'm going to ask you this question, and it's going to be the first question on the test. It's going to be a multiple choice test question. I'm going to tell you this straight up. I'm going to ask you, what's the direction of any centripetal acceleration in any force? What are you going to say?
Inward.
Inward. Right angle goes to the 90-degree vector. Don't choose outward. Don't choose a tangential line. It's inward. Okay? Is the velocity tangent to the circle? Yeah. But the force itself is inward. Now, so something has to be generating this force. So there's three options. Option number one, when we launched the satellite, we actually tied it to a big string, and it's orbiting around the Earth tied to a string. Okay, much like you all did with the rubber stopper swinging around your head. It's an option. Okay, I didn't say it's right, I'm just saying it's an option. Option number two is that we've actually gone and built a circular track out in space that the satellites are going to run on, okay, much like a road, okay, but it's perfectly clear, you can't see it, but that's what allowing it to go around, okay. That's the second option. Third option is what?
Gravity.
Gravity. I think that's our best option, right? Let's go with that. So here's what's important. The centripetal force needed to keep the satellite in orbit is equal to the gravitational pull between the satellite and the Earth. Now, at first I want to talk about how fast this thing is moving. So, what equation for centripetal force allows you to calculate centripetal force that involves velocity? Don't make this difficult.
mv squared over r.
mv squared over r, right? Now, here's what's important. Olivia, is that the mass of the Earth or is that the mass of the satellite?
Mass of the satellite.
Beautiful answer. Why?
Because that's the thing that's actually moving.
Nice. So this is going to be the mass of the satellite, okay? That is not the mass of the Earth, that's the mass of the satellite. Keep that in mind. That's the mass of the satellite. Okay. Now, that's the amount of inward force needed to keep this satellite in orbit. Now, let's talk gravitational force. So what do I need to calculate the gravitational force between the satellite and our rock? I need three things. No, not the weight of the rock.
Mass of the rock.
Mass of the rock. Okay? Mass of our Earth. What else? Mass of the satellite and the distance between them squared. Now, what's going to happen to the mass of the satellite?
Mass of the satellite.
Mass of the satellite's going to cancel out. So, guess what? On every problem I give you, do you think I'm ever going to give you the mass of the satellite?
No.
No. Do you know why?
It doesn't matter.
It doesn't matter. I'm also never going to tell you that it's silver or that it has solar panels or it has an American flag on this. No! Okay? It doesn't matter. Okay? It literally doesn't matter. So if you have something in a certain orbital radius, it could be, like for example, anybody know the name of the first satellite that was ever launched?
Sputnik.
Sputnik 1, okay, launched by the Russians, much to the dismay and embarrassment of the United States. Okay, and Sputnik 1 was basically about the size of like a basketball. Okay, it wasn't very big. It was literally just the size of a basketball.
He just
But we're all going, whoa, okay? Now the Russians are going to be spying on us, dropping bombs and everything else. That was a huge deal, okay? It's like, oh, man, how embarrassing. It would be like, it's like, literally, the equivalent would be like the varsity football team playing like Goddard Junior High and losing, okay? It was not a good time, okay? Because we're all going, oh, this is so embarrassing. Okay, so here's what's important. Whether it's the International Space Station, Sputnik, McGriddle, Mary, whoever, I'm never going to give you the mass of the satellite because it doesn't matter. Now, here's what I want to do. This is canceled out, right? These equations. So what I want to do is I'm going to cross multiply. So I'm going to have v squared r squared equals big G mass of the Earth times r. Now, I want to get v by itself, so I'm going to divide by r squared. And then I get big G, mass of the Earth, then what am I going to end up here?
With just a R on the bottom.
Just an R, it's kind of a pirate thing. R. I went from an R squared to an R, it lost me R. Okay. So, here's what I promise you is going to happen on the test. I'm going to take this equation, or this equation, or the one for period, which we'll get to later, and ask you to do dimensional analysis to make sure that the units work out. I promise you, it's going to be one of the questions on the test. It's either going to be this one, or the third one that we're going to get to today. And I'm going to ask you, do dimensional analysis to make sure that it actually works. I promise you, that's going to be a question on the test. So make sure before Thursday that you can do all these. So I'm going to work through this one right now so that everybody knows how you should do this problem. So, I got V equals the square root of big G times mass of the Earth over R. So, what are the units for big G? If you're not sure, look at your equation sheet. It's newtons, meters squared over
Kilograms squared.
kilograms squared.
Close.
And then the mass of the Earth is going to be in
Close.
kilograms. And then the radius is going to have to be in meters. Okay, so let's just start with this. The first thing you do is just substitute in the units. So Felix, what can I do here? Can I simplify this at all? What can I do? What about it? All of them or just one of them? Just one, okay? So I come in here and go, okay, I've lost one of my meters. Now, what else can I do, Felix?
Kilograms.
All of them? One of them, okay? So at this point, I'm going to regroup. So at this point, here's what I've got. I've got newtons, meters over kilograms. Everybody cool if that's what I have left?
Yeah.
Okay. Now, I can't cancel out newtons, but what can I do with newtons?
Split it into
Put it into
Kilograms.
meters per
second squared.
Now, that takes just the place of the newtons, but what's still there?
Meters per kilogram.
Meters and
Kilograms.
kilograms. Now what can happen?
You can cancel kilograms.
Now I can cancel out
Kilograms.
kilograms, and then I have
Square the
the
meter.
square root of meters squared over,
Second squared.
which is going to get me
Meters per second.
meters per second.
Wait, meters squared. Oh, we times that by.
Yeah.
Hang on. Oh, understood.
We're good? Everybody cool?
On,
What?
when you have just NM over kilograms, and then you go down.
Yeah, so all I did
Kilograms times.
was for the newtons, I just put this whole thing in for newtons.
Oh,
Because newtons are kilograms meters per second squared.
okay.
Make sense?
Yeah.
Okay. So then I take meters times meters, and that's how I get that, and that's still over second squared.
Okay.
So I promise you, this is what you're going to have to be able to do on the test. Okay? This one, the one for little g, or the one for big T, which we'll get to in just a second. Okay? I promise you, that's what you've got to be able to do on the test. So let me give you a hint. If I were you all between now and Thursday, I would do those problems at least 2 or 3 times so that you know how to do them. Okay? Because don't get on the test and go, oh man, Burkham didn't tell us we'd have to do this. I did. Okay. So, now let's actually work the problem. So here's the Earth. Here's the satellite. We're 200 kilometers above the Earth. I want to know V equals big G M over. Okay. Now, what are you going to do wrong in this problem? If you were to look into your own crystal ball and predict mistakes that teenagers would make on a problem like this, what do you think is the most common mistake you're going to do?
Forgetting the square root.
No. God, oh, if that was it, I'd be excited if that was it.
But in the wrong number.
Kilometers. You're gonna make them.
Well, first off, you have a radius that's in what?
Yeah.
Kilometers.
I'm gonna forget to do the square root.
So, Shively, what am I going to do?
Might want to convert that into meters.
Okay? Now, you have 200 kilometers. Here's the question. Do I multiply by 1,000 or divide by 1,000? Okay, if you divide by 1,000, what do you get? You get 0.2, right? So you're going to tell me that this thing is going to orbit above the Earth 0.2 kilometers above the surface of the Earth. 0.2 meters. This far.
The most intense game of jump rope.
No!
Like, coming around again, everybody.
Okay. So how about we multiply by 1,000 and get 200,000? Now, is that my radius?
No,
No, it's not.
that's just from
Radius?
the surface. That's just from the surface of the
That's
satellite.
from the surface of the Earth out.
So you need to add
We have to
the
go all
radius of
way
the Earth.
to the center.
Yes. So otherwise, now what else do we need?
Radius
of the Earth.
The radius of the Earth. You all have the radius of the Earth.
Yes.
Yes. So this radius, so somebody take the radius of the Earth, 6.3713, times 10 to the 6 meters, and add that to 200,000 meters. I think it's 6.5713.
Yeah. Yeah.
Yeah.
Now, when you do this, listen to me, listen to me, listen to me. When you're getting these sub calculations, don't round them, okay? When you're converting like hours to seconds or something like that, don't round them. Round when you get to the end, okay? Round when you get to the end. Okay, so now I've got my radius, now I'm off to the races. So, here's what we're going to do. We've got V equals big G, 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared. Mass of the Earth, 5.979. And what was the radius? 6.5713 times 10 to the 6th. Now, just before you touch a calculator, everybody step away from the calculator. Step away from the calculator. Let's just get a ballpark idea of where we're going to end up. Okay, order of magnitude. So if I take 10 to the negative 11 times 10 to the 24th, 10 to the 24th. Leslie, what do I get when I take 10 to the negative 11 times 10 to the 24th? 10 to the what?
Oh, 24.
10 to the 24th times 10 to the negative 11th. What exponent do I get? Do not touch a calculator. Do not touch a calculator. What's 24 minus 11? There you go. 10 to the 13th. So up on top, I've got 10 to the 13th. Divided by 10 to the 6th, and then I'm going to take the square root of all of that. So 10 to the 13th divided by 10 to the 6th gives me 10 to the
7.
So now I've got the square root of 10 to the 7th. Now, trust me, if you go through all the mishmash in here, this is going to work out to be 10 to the 3rd. So, trust me on this one. So when you have satellites in near Earth orbit, their velocities should work out to be something times 10 to the 3rd meters per second. Now, what's the order of magnitude of the speed of light?
10 to the 8th.
10 to the 8th. If you ever get a velocity approaching the speed of light, even 10 to the 5th, 10 to the 6th, let alone faster than the speed of light, which I've seen more often than I want to admit, you have done something horribly wrong, okay? Objects in near Earth orbit, whether it's the Earth or the Moon, are going to be orbiting with the velocities of 10 to the 3rd, okay? So that's a nice little check that you can do. When you calculate that velocity, look at it. Oh, is that 10 to the 3rd? Oh, right. Okay, cool. If it's not, something went wrong, okay? Something has gone horribly wrong, okay? So don't be afraid, and I realize here's your step. Punch numbers into a calculator, look at the oracle, and write it down. The only thing I'm asking you to do is throw in a little substep where you, before you write it down, you look at what the oracle tells you and go, might the oracle be wrong? Okay? And I realize that might be against the religion of some of you to question the oracle. It's okay. Your calculator doesn't care if you question it. Trust me. Okay. Now, somebody actually crunched the numbers. This is why it's handy to have these numbers stored in your calculator, because then you don't have to punch them in every time.
Okay.
So, what'd you get? Huh?
7.91 times 10 to the 3rd.
7.91 times 10 to the what?
Here it got 7.90, but yeah.
Yeah, I also
They're
got
close.
7.91, so unless you're wrong.
Yeah, I guess.
Sorry, big man.
But you- yeah, he got 7.91.
Everybody cool?
Yeah.
If you're not getting this, something has gone horribly wrong. Now, what do you think you are going to do wrong when you get to this number? Or, excuse me, when you get done with this calculation, what do you think you're going to do wrong? What are you going to forget to do? No.
What do I do?
The square root?
You're going to forget to take the square root. So if you forget to take the square root, you can have like 10 to the 6th or 10 to the 7th. And that's what you're going to do wrong. You're going to write that down and I'm going to go, really?
You do
Come on.
minus.
So, everybody cool with how you got this? Now, what if you want to make this velocity that you think, well, that's a little bit too fast, okay? If you wanted this thing to go slower, would you put it into a higher orbit or a lower orbit?
Times m, then divided by r. Because
what
we
I
did
did.
all of it in one shot.
I want to make it go
You did it all
slower.
in one shot. They did it like separate.
Yeah,
so
you
this rounded
boost it
in
into
this
a higher
sense.
orbit. So here's how this deal played out. Y'all heard of the Hubble spaceship? Or the Hubble telescope? Okay? So a little embarrassing thing that happened when we launched the Hubble Space Telescope. And it's this multi-million-dollar thing, and this is going to revolutionize astronomy and all this good stuff, and it was spent millions of dollars and all this hoopla. And they actually launched it from the space shuttle, so they carried it up in the space shuttle and deployed it from the space shuttle. Well, the problem is when Hubble first really started to operate, the pictures were fuzzy, okay? So it's kind of like if I take my glasses and I hold my glasses up here, notice that they cast a shadow on the screen. But if I bring them closer, that shadow disappears because now I'm within the focal length of the lenses. So if I'm out here, it looks like they're dark. But when I get closer, and if I get just that right point, then everything's into focus. So basically what happened was the optics were screwed up on the Hubble Space Telescope. And they were here, and they weren't getting a clear image, and it should have been here. Well, unfortunately, this thing was in orbit traveling at about 7,000 meters per second, and they're going, oh, ruh-roh. So, what they did is that, this is back when we had an operational space shuttle fleet. So, they put the space shuttle into a lower orbit because it was going faster. Okay, so it had to catch up to the Hubble. Then, they would fire the engines, and then they would move into the higher orbit of where the Hubble was orbiting. Then they went out and basically took out one set of lenses and corrected and put the lenses back in. So they had to do this big spacewalk, and then it worked marvelously. Because initially NASA was going, oh God, we have completely screwed this up. And so because of that, now we have these magnificent pictures of the space shuttle and all this good of outer space, and life is good. Okay, so you got that equation. Life's good. Okay. Now, let's go back to
Yes.
an orbit. Now I want to look at orbital period. So what's the way to calculate centripetal force that involves mass, radius, and orbital period? Starts with 4.
4.
So the centripetal force would be the mass of the satellite, 4 pi squared r over
T squared.
T squared equals big G, mass of the satellite, mass of the Earth over r squared. Now, again, what's going to happen to the mass of the satellite? It's going to cancel out. You see a recurring theme.
Yeah.
Yes, mass of the satellite doesn't matter. Does the mass of the Earth matter? Or the moon or whatever you're orbiting? That matters, okay? Sometimes matter matters, sometimes it doesn't matter. Okay? In this case, mass matters. Okay. So what I want to do is cross multiply. Now this is the pirate's favorite equation. So I got 4 pi squared r cubed. Okay? So this is the pirate's favorite equation because you get r cubed. And you get big G, mass of the Earth, and T squared. This is what's on your equation sheet. Okay? This is what's actually listed. And the reason that I listed it like this is because this is like the Swiss Army knife of equations. Okay? Because once you get here, you can solve for radius, you can solve for mass, you can solve for period. Okay? So this has 3 different variables that you can solve for depending upon the situation. So in this situation, I want to get t by itself. So what can I get to get t by itself? Math. I want to get t by itself.
Okay. So there's a few steps that you have to take, right?
There's 2.
At least. You're going to divide by G,
So I'm going to
right?
have 4 pi squared r cubed.
Uh-huh.
Divide by,
G,
yeah,
and then also mass of the Earth.
okay?
And then you're going to want to take the square root of that.
You're mad. Yes. That's my son.
That's
My son. Did he say that?
Matt for son, 20.
Yeah.
20.
Exactly what I said.
Okay. Now, we're going to use the exact same numbers, 4 pi squared, and then it was,
I don't want
what was it, 6 point, what was that radius, 6.5317?
713. 57.
5713.
Yeah.
Times 10 to the 6 meters, but that's going to get cubed. And then we're going to divide by 6.67 times 10 to the negative 11th. And then the mass of the Earth, 5.979 times 10 to the 21. Now, when you're actually in the throes of this assignment, you don't need to write out big G every time, okay? You don't need to write out the mass of the Earth every time. You can just put big G and M, okay? If you really want to write it out, you can. Now, again, let's just do a quick order of magnitude. 10 to the 6 cubes give me what? 10 to the 18th, right? So up on top I got 10 to the 18th. 10 to the negative 11th times 10 to the 24th gives me 10 to the... So I got 10 to the 18th divided by 10 to the 13th, which gives me about 10 to the 5th. Square root of that, again, is going to get you about 10 to the 3rd. So here's what's important. When you calculate orbital periods in near Earth or lunar orbit, the order of magnitude should be 10 to the 3rd seconds. So this is why this is easy to remember. Your orbital velocity should be 10 to the 3rd. Your orbital periods in seconds should also be 10 to the 3rd. Okay? So you don't, if you just remember 10 to the 3rd and that's what you should be getting, that's all you need to remember. Okay? Near Earth orbit, near lunar orbit. Now, obviously, if you're way out in deep space, that might change. But generally, it's going to be 10 to the third. Certainly not 10 to the sixth, and certainly not longer than the universe itself has existed. I've gotten those answers as well. So, somebody run the numbers. Let me know what you get. Don't forget the square of pi, and then take the square root.
Yeah, this is from the center of the Earth all the way out to 200.
Oh, you're right, you're right. So yeah, I'd agree with your answer then. Yeah. Yeah, so 5.30 times 10 to the third. Yeah. 5.30 times 10 to the third.
5.30 times 10 to the third?
Yeah.
Everybody cool with that?
Not sure yet.
It depends on how you enter it into your calculator. If you do it all in one shot, it doesn't give you
Okay,
a
we'll
round.
finish this up tomorrow, but yeah. No, you don't have any homework.